Today we're going to tackle this problem. What is a pH at the equivalence point when you mix a strong acid with a weak base? So first we start by writing a net equation where instead of writing HCl, I just wrote hydronium because that's what's net reacting. And in our ice table, I like to start with adding the moles in here, which is concentration times the volume as liters, which will give us 2.5 times 10 to the negative 3 moles. I like to do it in moles because, as you can tell, that later on this is going to be a greater volume, so there are other steps that we have to take later on. So at equivalence point, that means both of our reactants are at stoichiometric equivalence, so they have the same amount of moles and they completely react one with another to completely neutralize one another. So we should have 0 here. Likewise, the conjugate acid that is formed will also increase by the same amount stoichiometrically by the same amount as the amount as our reactants have been consumed. Okay, so we're not done here yet because this is our conjugate weak acid, which will further react with water to give us our pH. Because in the first equation there, what we had was a water is neutral, and then we had a weak acid. So now we want to find what is the pH that is caused by this weak acid. So we would need to write out this further reaction with water. And that will give us the conjugate and the hydronium. Notice here I still used moles, but here you can use the concentration, but you have to make sure that it's moles divided by 50 millimeters. You can put the concentration in here, but I'll do that in a bit. You can put it in here because all of this is one solution and we're not adding any additional significant volume. So we don't know by how much this will react with water. And now we have to use our Ka constant. Remember, if they were producing a hydroxide instead, you would use a Kb. Now Ka, the special thing here, it has to deal with the concentration of reactants divided by the concentration of products divided by the concentration of reactants. So what we want to do here is to actually convert this into concentration. And this is all together in a solution of 50 millimeters. You have to be really careful here. It's really easy to forget about the volume, which will give us a concentration of 0.05 moles per liter. Now we can throw it into our Ka here. Now the Ka, acid dissociation constant for the ammonium ion into hydroxide, is 5.6 times 10 to the negative 10. So the big takeaway in this part is, remember the concentration has to come from the final volume. Okay, so you want to either convert it here or you want to convert it here. Just before you throw it into your Ka, remember that all of this should be in concentrations, not in moles. And also if it's hydroxide being produced, make sure you are writing Kb instead. Kb is Kw divided by Ka. Okay, now because our Ka is very small, that means we can just omit the x here, but that means we have to check our assumption later. So we can omit this for now. Although on an exam you do want to write something like 0.05 minus x is just basically the same as 0.05 since x is so small. So X would give us around 5.29 times 10 to the negative 6. And this is already in concentrations, good. And this is a concentration of hydronium. Now we want the pH. The pH is negative log of the hydronium concentration, which will give us a pH of 5.2728. And there you have it. So big takeaways, aside from the things I've already highlighted in red, if you got the hydroxide concentrations, you would get a POH, and to get the pH, it would be 14 minus POH. Remember to use concentrations here before throwing anything into Ka. Make sure what you're throwing into Ka is already the moles divided by the total concentration, divided by total volume.